So step 4 is about specifying the conditions under which the null hypothesis is rejected and the conditions under which it is not rejected. So this decision rule here is a statement of specific conditions under which the null hypothesis is rejected and the conditions under which the null hypothesis is not rejected. And we have a region or area of rejection that defines the location of all the values that are either so small or so large that the probability of them occurring under the null hypothesis is remote.
Really quick, the positioning of the tail on alpha is determined by the scenario we have. So like in that one, it's pushed all the way to the positive side. There's other scenarios where it's like split between positive and negative side, and others where it's just pushed to the negative side.
Correct, yes. So this is a one-tail situation. So we're trying to figure out just, is this greater than? So the null hypothesis for something like this would be, is the x bar greater than mu? And then the alternative hypothesis, x bar is greater than or equal to mu. And then the alternative hypothesis would be x bar is less than mu. So a lot of times we're going to have stuff that looks a little differently because we're going to have two tails to them. So the ones that look a little differently look like this. So this is a one-tailed, and this is a two-tail. So both of these are looking at a 95 probability, but one of them has a null hypothesis that is greater than, and the other one has a null hypothesis that is equal to. So they both they have the same levels of significance. They have the same area under the curve that's telling us the probability of rejection. But on a single tail test, it's focused on just one of the tails. And let's zoom in real quick on this, right? So what is this telling us? What is this telling us? So the region or the area of rejection defines the location of all the values that are so large in this particular instance that their probability of occurrence under a true null hypothesis is remote. So if we find that the z, right, which is just the number of standard deviations the sample mean is away from the population mean, if we find that it's over 1.645 of those standard deviations, right, if the difference is more than 1.645 of the difference, and we're only testing if it's greater than or equal to, then we need it to be less than 1.465 standard deviations. We need that difference to be less than 1.645 in order to make a statement about the null hypothesis and our rejection of it. So this value separates the region where the null hypothesis is rejected, this whole region here is that where the null hypothesis is rejected, that they are equal to each other. They're too many standard deviations away in the sample, compared to if it's any other value below that, it could be negative, 3, right? Or it could be 0, or it could be 1.5, or it could be negative 0.5, right? If it's any one of those values, then we don't reject the null hypothesis. We don't have sufficient evidence to say that the population mean is statistically significant. And that's where the kind of term statistical significance really starts to make sense and come into focus, is in this chapter, right? Statistical significance is a specific set of conditions that talks about how likely it is for this to be different from that in the population, given the information we have about the sample and about for this particular one, about the population standard deviation.
We're never going to have to concern ourselves with a situation where one of the tails gets cut off by logic. Like if we have a mean of 3 inches of rainfall, you can't have less than 0 inches, so one of the tails gets cut off. We're not going to have to worry about that.
No, we're not going to have to worry about that. That's a great point, though. That's some critical thought there, right? So sometimes we might have normal curves where theoretically they extend over parts of the value that don't make any sense, like having negative rainfall. Absolutely. Although one could argue that evaporation is negative rainfall, right?
Then we're going to have to calculate both of them.
I complicate your complications there.